Hi there, learners. Welcome back to Chemistry. My name is Adam Parker. I'm so glad you're here today. Today, we are talking about part one of a two-part series that we're going to be talking about matter. So it's M-A-T-T-E-R. Matter is one of those things that I think a lot of people initially have some confusion about because it's a little strange and hard to kind of wrap your head around when it's something new. So, what is matter? Let's start with that. Matter is what is making up everything you look around. So you look around the room where you're in and you see, the walls, you see the floor, you breathe the air, you have a, cold drink when you're that you're surrounded by. All of that, virtually everything you see around you is made of matter. So matter is anything in the universe that has mass, that can make up something. So basically, you can take that matter and it can be used in lots of different ways. And so when scientists talk about looking at something, classifying something, one of the big things they look at is, how do I classify all this matter? If the world and the universe is made of this stuff, how do I do anything with it? Because it's one thing to say that this pen is made of matter, but what do I actually do with that? So today we're going to be talking about what is matter, some of the theories that are kind of governed as we've understood matter, and what we're going to do with it. So this should be really helpful for you. So definitely want to take notes and be referring to the text that I'm using is Discovering Design with Chemistry. And so this is a great book from Dr. Weil. I suggest you take a look at it if you haven't already. So two major things of matter. When we talk about matter, we have what we might call a pure substance and a mixture. Now, pure, you hear pure, right? You think like pure spring water, purify. What we mean by pure is that it is just one thing. So you think about if you had a big container full of M&Ms, right? So if they're all green M&Ms, every single one is the same. And everything inside the container is exactly the same. They're all green M&Ms. Then you would say you have a pure substance. It's all green M&Ms. Now, obviously the inside's all the same, but right? They're all green. They all look the same. We could say that's a pure substance. Now, if I got just a bag of M&Ms and I poured it into my hand, are they going to be all green? Probably not, right? They're going to be different colors. They're going to be brown, they're going to be blue and yellow, or whatever the current color is for M&Ms, right? They change it every few years. But that would be a mixture. And we say mixed because they're mixed together, right? And you use this term. You've heard about mixtures, right? So when we say that, is that there's two or more pure substances mixed together. I hope that makes sense. But that's the simplest way to think about it. You kind of look at your salt and pepper shakers on your table, right? So inside the salt shaker, you have sodium chloride, table salt. Inside there, just looking at it, it's only salt. So that would be a pure substance, right? Now, you also have the pepper mixture. So if you put the pepper and you put the salt and you mix them together and you put them on your plate to put on your food or whatever, well, now you have a mixture of salt and pepper. And so that is a mixture. Very simple. Not super complicated, but something that you really want to think about is this really helps us with classifying matter so that we understand the different types of things that surround this world around us, right? Okay, so that's kind of what we're going. So we've got a cool experiment in here that I'm going to be putting how to do that. It's real simple, but I want you to do it at home. Really illustrates mixtures and pure substances. So for like comprehension here, an ice cube. Is an ice cube a mixture or a pure substance? So you get ice from the freezer, right? You got a piece of ice. Well, ice is frozen, right? But it's frozen water. Water is two hydrogens and an oxygen, H2O. If you ever heard that before, that is the ice cube is made of water. It's basically a pure substance. Now we could argue if there are some minerals in the water, but for the sake of argument, that would be pure, right? But if you go to the kitchen and you get a bowl of cereal and you put milk on it, is that a mixture or is that a pure substance? Well, the cereal is one and the milk is another, and you can separate them, right? So it's a mixture. So simple things like that to keep that straight. Now, you're going to learn some big words here, okay? So these are two types of mixtures, and this is going to be something that is super helpful for you. So one is a homogeneous mixture or a heterogeneous mixture. And sometimes you'll hear the term homogeneous or homogeneous. That's two different ways to say it. So get to work on your Latin today. So homo means the same. Genus or genius is type. So a homogeneous mixture means that the entire mixture is consistent. It's the same all the way through. It's a mixture, but it's the same all the way through. So you could think of it like chocolate milk, right? You have milk, and then you put your syrup in there, right? You ever make chocolate milk? When you stir it up, the whole thing is chocolate milk. It's not like milk on the bottom and then chocolate, right? And it's not have chunks floating in it. Now, you know, if you don't mix it very well, right? Or think of if you have a cup of coffee and you add some cream to it and you mix it up, well, the whole thing is now the same. The cream has distributed through the coffee, so now you have cream coffee, right? That is a homogeneous or homogeneous mixture, okay? Now, a hetero is another Latin prefix that means different. So if you think homogeneous or homogeneous is all the same, heterogeneous or heterogeneous is sometimes how you'll hear someone say it. If I say it differently, just roll with me. You can assume that means different. So that would be an inconsistent mixture. And this goes back to like our thing about M&Ms, right? If I randomly grab a handful of M&Ms from a big bowl of M&Ms and they're all mixed in there, every handful I grab will not be exactly the same, right? There's going to be little differences. Even though they're mostly the same, they won't be exactly the same. So that would be a heterogeneous. So that's a simple thing. They have a good example in the text talking about salad dressing. If you like Thousand Island salad dressing or ranch, if you look in there, it's a mixture, right? You've got seasonings, you've got cream, all that stuff in ranch dressing. I know I have nieces and nephews that want to dip everything in ranch dressing. I don't really understand that. But hey, if you get the ranch dressing and you look at it, you can see that it's definitely a mixture, but it's not consistent. Sometimes you have a little more spice, sometimes you have a little other, and some a little less, a little more. That's a heterogeneous mixture. So you're going to be classifying some things. So look around the air around you. So take a deep breath, go. That's air you're breathing, right? So your air that you're breathing, air is a homogeneous mixture, at least general air. Like obviously in a room, you know, I'm in my office right now. If I closed all the doors and sealed everything off, well, then the mixture in this room would change over time, right? But generally, the air on Earth is a mixture, and it's very consistent around the world. It doesn't change very much. It's about 78% nitrogen, 21% oxygen, and then you have some trace elements like carbon dioxide and argon and neon and stuff like that. But you use the oxygen to breathe, right? And nitrogen is there for pressure balance. You know, you don't do much with it as far as your breathing, but it's very important in the cycle for plants and animals. You need nitrogen. So that mixture is very, very important. So there's a couple different things there. Let's see, we got a few things talking about milk. I want to make sure that we talk about that. Now, we mostly been talking about liquid mixtures, but you can have a solid mixture or a gas mixture, right? We talked about air as a gas. We also have solid mixtures. So you think about if you've ever been into like digging rocks in your yard, right? Most of us go through a rock phase. In the rocks, you have mixtures. They're not just one rock. Now, gold, like we talk about solid gold, 18 karat gold, right? Gold is an element. If you look on the periodic table, it's AU is gold. Gold is a pure substance. So like when someone has a gold ring, now mine's made of titanium, which is another pure substance. That if you get rid of everything else and you have just gold, that's a pure substance. The thing about gold is also very, very soft. So most rings are actually an alloy. They have some gold and they have some others. So they have some good examples in here talking about, you know, zinc oxide and how you make that. So definitely take a look at that. But there's a couple things we just want to talk about that goes a little further. So the reason we talk about all this, and we're using all these definitions, is there's a very important principle that I want you guys to really focus on and listen, okay? When you have mass, the amount of matter in the universe is consistent. You know, you have the stuff in the wall, right? All this matter around me, around you, the amount of matter in the universe is consistent. It's neither being created nor destroyed. It is being transformed. In the same way, when you are looking at a system, and a system could be this room, it could be the beaker if you're doing an experiment, it could be inside, you know, a flask or however you're doing it. The system is whatever you're going to study. The amount of matter in a system, if you like close it, right, is consistent. You don't destroy the matter and you don't make the matter. You transform the matter. So when you have something that is a mixture and you separate it, or you turn something into a mixture, or you have a reaction, the amount of matter is the same. We call that the conservation of mass. That mass is always consistent. Now, conservation isn't like reduce, reuse, recycle, right? When we hear conservation, we mean that it is conserved and that it is not wasted, is that it is held on to. So the really obvious thing with this, and this goes back to Lavoisier, talked about the conservation of matter, is think about a fire, right? So you ever have a fire pit, especially in the fall, it's really nice to go out and have a fire pit and roast a marshmallow or something like that, is you take wood, it has a certain amount of mass, right? And you make your fire pile and you put some paper in there, right? And you measure that and you light the whole thing on fire and it burns. Now let's say you could capture everything that came from that. So, you know, you get the little sparks and you get the ash and it releases gases and stuff like that. In that system, if you captured all that, you would find after you burned it, you actually have more mass than the wood you started with. So where's the extra mass coming from? The wood has a certain amount of mass. Fire is energy. It doesn't really have much matter in it, right? Because fire is, you know, energy, heat. So where'd it come from? The extra mass. Well, it came from the air. It needs oxygen to burn. You've ever heard this, right? You got to have, you know, your fire triangle, right? You got to have fuel, you got to have an ignition source, and you got to have oxygen. The oxygen came from the air, combusted, burned in the fire, and made the ash and made all the other things, made water and the carbon dioxide that comes out of it. So, but again, all the matter that is there at the end was available at the beginning. All it did was transform it. So we're going to do several examples where you're going to be studying the conservation of mass. So a couple more vocabulary words, for lack of a better term. So when we're going to be studying the periodic table more in depth as we get through this class, we haven't really tackled that yet. But on the periodic table, it's this big table that has what they call elements. So E-L-E-M-E-N-T, element. So we talk about something that is elemental, something that is, you know, elemental, critical. Elements are the simplest form of matter that maintains their properties. So you sometimes says it can't be chemically broken down to simpler substances. So an element is like carbon, oxygen, nitrogen, zinc, sulfur. All those are elements. So we have what we call is an elemental of sulfur. We can't break it down anymore and it's still sulfur. We could break it down more, but then it's no longer sulfur if we start messing with it beyond that point. Does that make sense? So we haven't really gotten into atoms. We're about to. An atom of carbon is always the same. But if I go smaller than an atom of carbon, it's not carbon anymore. Okay? So now a compound, and you've heard this term probably, compound just means sticking together. Compound, more than one. So a compound is something that is indivisible to make what it is, but it is made up of elements. Okay? So this would be something like carbon dioxide. You've heard of carbon dioxide, right? It's what you breathe out when you exhale, right? And this is what plants use to make food. So we exhale carbon dioxide, the plants inhale carbon dioxide, they exhale oxygen, and you inhale oxygen, and you have the whole circle of life, right? I'm sure you've probably learned this, back in middle school or whatever. Carbon dioxide is made of one atom of carbon and two atoms of oxygen. Carbon dioxide. So that is a compound. If you broke it down smaller than the atom of carbon and the two oxygens, it's no longer carbon dioxide. It could be other things, but it doesn't behave and it doesn't have the properties of carbon dioxide anymore. So compound, 2 elements or more. Pure substance is 1 element, okay? So we talk about, there's an example in here about zinc sulfide. So that is a very common ore. Ore is a metal that you dig out of the ground, right? Gold ore, iron ore. Zinc sulfide is a compound, an ore. Now, zinc sulfide can be separated into zinc and sulfur. Zinc sulfide, I might have said oxide, but I mean sulfide. Zinc sulfide, zinc and sulfur. And they have a great example that if you have 100 grams of zinc sulfide and you separate it into its elements, well, now you don't have a compound, now you have elements. And you end up with basically 33 grams of sulfur, 67 grams of zinc. So you conserve the mass. The amount of mass is the same. That's that whole trick about moving things. There's a few things in here about different types of metal that I want you to look over. Malleable and brittle. There's different properties of metals, but I'll let you take a look at that. But here's what you want to think about. I want you to visualize this, is matter, it's anything that has mass and takes up space, okay? So mass is, actually has atoms. It has something making it up, and it takes up space. It has some volume. Might be really, really small, but if it has any volume at all, it's matter, okay? Then we split and we have pure substances and we have mixtures, right? Then within mixtures, we have homogeneous or homogeneous mixtures and heterogeneous mixtures, right? We already talked about that. Within a pure substance, I have an element and I have a compound. Now, what's the difference between a mixture and a compound? A mixture is several pure substances mixed together, right? And I could separate them if I wanted to. We talked about cereal and milk. If I'm having cereal, I could pour the milk out and pull the cereal out, and it might get kind of soggy, right? But I could separate it. If I have carbon dioxide, that is a compound. It's not a pure substance, but I can't separate the carbon from the oxygen without doing it chemically, right? I can't physically separate them. That's kind of the difference. So there's some great examples of things in here. So definitely want to spend some time thinking about that. Now, next part we're going to talk about is what is called the law of definite proportions. A lot of words there. Remember, we talk about a scientific law. A law is something that is objectively provable, that we have shown scientifically over and over and over again that it is true. Now, all it takes is one time to violate the law and the law is not true anymore. But as far as we know, this law is true. So keep that in mind. Definite means for sure, right? Stays the same, consistent. Proportions. Proportions is relations of one thing to another, right? So what you talk about is if I have carbon dioxide, right? We talked about it has a carbon and 2 oxygens. That means no matter what, the amount of carbon and oxygen in carbon dioxide is always the same. It has definitive proportions. Otherwise, it's not carbon dioxide. It could be carbon trioxide or something, or carbon monoxide, which is really dangerous, right? You've probably heard of carbon monoxide poisoning. So that oxygen being in the right place, the carbons being in the right place, makes a difference. So that's what we mean by definite proportions. So I want to talk through an example. So I'm going to share my screen really quick, and we're just going to talk about what does it mean to have definite proportions. So let's read this over. So a chemist uses 32 grams. We're going to say 32 grams of carbon. So that's big C, right? And then you have 44 grams, so it's 32 grams of carbon and 32 grams of oxygen. And that's just O. Big O is oxygen, right? They're going to make 44 grams of a gas. Okay? Now, so interesting. But there's going to be some leftover carbon. So we know that I'm going to use the oxygen but I'm not going to use all the carbon. There's going to be some leftovers. If this scientist, she wants to make 110 grams of that same gas and have no leftovers at all, how much of carbon and oxygen should she use? So we have to use the law of concentration of mass, or mass conservation, and we're going to use definite proportions. So here's how we want to set this up. So let's start with, I started with a certain amount of mass, right? So I had 32 grams of carbon and 32 grams of oxygen. That's mass, right? Grams are measuring your mass. So I started with 64 grams of material, right? Now, we know that she ended up with 44 grams. So if I started with 64 and I ended with 44, how many am I missing? Right? 20 grams. 64 minus 44 is 20 grams missing, right? So our question is, what happened to the 20 grams? Where'd they go? So we started with 32 grams of carbon. We said that the oxygen was used up and the carbon was not, right? So that means this 20 grams is carbon. Does that make sense? The oxygen was used, the carbon was not. So if I started with 32 grams of carbon, right? 32 grams of C minus 20 grams left over, right? That means I used 12 grams of carbon. So you see that that's that conservation of mass. I have to conserve it. It's got to go somewhere. So it's still laying around. So we know the recipe. So what do we know? We know we used 32 grams of oxygen and we used 12 grams of carbon. That sounds like a recipe for making something. You ever do a recipe in the kitchen and they say you got to use a cup of this, 3 cups of this? This is a chemical recipe. So we know that 32 grams of oxygen and 12 grams of carbon is going to make 44 grams of whatever the gas is, okay? Now, it could be carbon monoxide, it could be carbon dioxide. We'd have to see exactly what it is. But that's a start, right? And we haven't really gotten into moles yet, so we're not going to talk about that. So now we know 44 grams is the magic number, so I'm going to erase this really quick. Now, here's what we want to know. I want 110 grams of this gas. Well, I know how to make 44 grams, and I know the recipe for that. So now I'm going to use my law of definite proportions, okay? Proportions, if you learned this in math, you would have done this in Algebra 1, maybe a little earlier, is if I know a number at one value, I can scale it up or down using a proportion. So we're going to make a multiplication factor. So you might remember this from algebra. So I'm going to put my bigger number, 110, on top. I'm going to put 44 on the bottom. 110 divided by 44 is 2.5. You guys see how I did that? So that tells me that instead of just 44 grams, I want 110. I need to multiply everything by a factor of 2.5. This is the definite proportion working in our favor, okay? So we're going to use that. So I know that I use 12 grams of carbon, right? And 32 grams of oxygen. I'm going to put an O and a C. Well, I got to multiply it by my factor, which is 2.5. 2.5, 2.5. Remember, I use the same factor on both examples so that I can scale it up. So that's going to be 12 times 2.5, which is 30 grams, and 32 times 2.5, which is 80 grams. Does that make sense? So what we know is, so if I want to end up with 110 grams of gas, what I need is 80 grams of oxygen and 30 grams of carbon. And there it is. Now, does that make sense? That's pretty straightforward. It's not that complicated. So you're going to work a couple of examples like this, where you're going to find a formula and you're going to scale it to find exactly what you need either way. Okay, so let me go back to the main page here. So what we want to talk through is, whoa, sorry, dropped my thing there. So you're going to have some problems working off this simple concept of comparing homogeneous mixtures and heterogeneous mixtures. And you're going to work through a few of these scaling examples where you're going to find a formula and you're going to scale it up or down. It's not that complicated, and you're going to do great. So we'll be back in just a few minutes to talk through part 2. Have a good day, guys.